Welcome to a deep dive into the life and work of Lord Kelvin. You might know him from, your science classes, like the Kelvin scale.
Absolutely, but there's so much more to him. He's not just a unit of measurement.
Right, he's like a scientific giant.
Yeah.
We've got some biography excerpts, timelines of what he did, some really interesting stuff. And today, we're going to sort of uncover why his work was important and how we still see its impact today.
Yeah, for sure. And what's fascinating is how he bridges that gap between the abstract scientific theory and real-world impact.
Yeah.
He wasn't just content with equations on a chalkboard. He wanted to see these ideas play out in the world, and he often made that happen himself.
So where do we even begin? William Thomson, who later became Lord Kelvin, was a bit of a prodigy. I mean, starting university age 10.
It's mind-blowing.
Yeah, at the University of Glasgow.
Impressive in itself, but even more so, think about this. By age 12, he's winning astronomy prizes for essays that sort of foreshadow his lifelong fascination with the natural world.
Right.
Combining that with a mind for math and physics, that's the recipe for an incredible career.
That's true. I wonder what kind of education system they had back then to nurture that kind of talent.
Right.
And get this, by 22, he's a professor teaching a class he himself had been a student in just a few years before. Talk about a fast learner.
Unbelievable, right? And what's interesting is even in his early years, we see these seeds of his later work, like his engagement with Fourier's theories on heat conduction, that sort of planted the ideas that later blossomed into his groundbreaking contributions to thermodynamics.
Thermodynamics. Okay, for those of us who haven't cracked open a physics textbook in a while, can we just get a refresher on what that even is?
Of course. In the simplest terms, thermodynamics is the study of how heat, work, and energy relate to each other.
Okay.
And Kelvin was a master of this field, making huge leaps in our understanding of how energy flows and transforms. These are fundamental principles that govern everything from engines to even the climate.
And this was all happening in the mid-1800s, right?
Yeah.
Wasn't that a time of big shifts in how scientists were even understanding heat?
Absolutely. Back then, the prevailing theory was that heat was a kind of fluid called caloric.
Okay.
And it was thought to flow from hotter objects to colder ones. But then along came James Prescott Joule, who proposed this radical idea that heat was actually a form of energy related to the motion of molecules.
So instead of some invisible fluid, heat was actually about things moving and vibrating at a tiny level.
Exactly.
Wow, that's a pretty big shift.
Yeah. And not everyone was ready to embrace that new paradigm. In fact, even brilliant minds like Kelvin were initially skeptical of Joule's ideas. He was more aligned with the established Carnot-Clapeyron theory, which was based on that caloric fluid idea.
So how did he go from being a skeptic to one of the pioneers of thermodynamics? That's a big jump.
Well, what's so remarkable about Kelvin is that he wasn't afraid to challenge his own assumptions. He really dug deep into Carnot's work, refining and rethinking those existing theories. And it was through this process that he stumbled upon one of his most groundbreaking concepts: absolute zero.
Absolute zero. I remember that from school. But I don't know, it always sounded kind of abstract to me. What does it actually mean?
You have to understand, this was revolutionary. Before Kelvin, temperature was relative, just comparing how hot or cold something felt. He gave us an absolute scale tied to the fundamental nature of heat itself. It was a conceptual leap.
Yeah.
And this wasn't just about better thermometers, it was about unlocking the secrets of thermodynamics.
Right.
It's imagine trying to understand how an engine works without knowing how much fuel you're putting in.
Okay, I'm following you. So Kelvin figures out absolute zero, this fundamental limit of coldness. But he wasn't just an ivory tower theorist, right?
Yeah.
He was also all about putting science into action. And this is where the transatlantic cable comes in.
Absolutely.
I'm picturing him on that ship, battling storms, battling scientific rivals. Was this a common thing back then?
There was certainly a lot of competition, strong personalities in the scientific world back then. But the transatlantic cable was an undertaking of unprecedented scale and ambition. Laying a cable thousands of miles long across the stormy Atlantic Ocean in the 19th century.
Right.
It seemed almost impossible.
Yeah. And Kelvin wasn't just there to cheer them on from the sidelines. He was out there on those expeditions, using his knowledge to solve real-world problems.
Right.
I mean, the pressure must have been immense. Imagine having the fate of, global communication resting on your shoulders.
That's exactly what makes Kelvin so compelling. He wasn't afraid to get his hands dirty, to work alongside engineers and face setbacks. He was instrumental in calculating signal speed, designing the cable itself, and even inventing devices to make this this communication dream a reality.
Like the mirror galvanometer, right?
Yeah.
That sounds pretty high-tech for the 1800s. What did that even do?
It wasn't just a lab toy. It was so sensitive that it could detect these tiny electrical signals sent across the Atlantic. It made transatlantic communication possible. Kelvin's genius was in understanding the physics and then translating that into a practical solution.
So he's helping connect continents with this incredible feat of engineering.
Mm-hmm.
Where do we go from here? Did his work on the cable lead him in any new directions?
It wasn't just about connecting continents. It got him thinking about deep time.
Deep time.
Yeah, I mean, that cable's laying on an ocean floor that had formed over eons.
Right.
It got him thinking about the age of the Earth itself.
So from laying cables, he starts pondering the age of our planet. What a leap.
It might seem like a leap, but for Kelvin, it was all connected. He was a physicist at heart, and he saw physics at work everywhere, even in the seemingly static rocks beneath our feet.
So how did a physicist go about figuring out the age of the Earth? Did they have carbon dating back then?
No, not quite. Kelvin approached this question with the tools he knew best: thermodynamics. He reasoned that the Earth must have been cooling down from a molten state. And by estimating its current temperature and the rate of cooling, he could calculate, how long it had been since that solidification.
So he's basically applying the principles of heat loss to the entire planet. That's thinking big.
Exactly. And his calculations, based on the physics that he knew at the time, led him to an estimate of somewhere between 20 and 40 million years old.
That sounds pretty old. Was that a controversial number back then?
It was incredibly controversial. You see, around the same time, Darwin's theory of evolution was gaining traction.
Right.
And Darwin's theory needed far longer timescales, for the slow, gradual processes of natural selection to play out.
So you've got the scientific showdown brewing, physics versus biology. Kelvin, with his calculations, seemed to be saying that Darwin's theory couldn't possibly be true.
Right.
That must have ruffled some feathers.
It certainly did. And to make things even more complex, Kelvin was a creationist.
Okay.
But it's important to understand what that meant in the context of the 19th century.
Right, because when we hear creationists today, we tend to think of a very specific set of beliefs. But back then, it wasn't so clear-cut, was it?
Exactly. Kelvin believed in a divine creator, but he wasn't a flood geologist,
Right.
He didn't believe that the Earth's geology was shaped by a single catastrophic event. His creationism was more nuanced. It was intertwined with his understanding of thermodynamics and the idea of a universe slowly running down.
This is where it gets really interesting for me. Kelvin had this concept of the heat death of the universe. It sounds pretty bleak. Can you explain that?
Imagine a cup of hot coffee left out on a table. Eventually, it cools down to room temperature, right?
Yeah.
The heat spreads out, becoming evenly distributed. Kelvin saw this happening on a cosmic scale.
Wow.
He believed that, according to the laws of thermodynamics, all energy in the universe would eventually be, evenly spread out, with no more potential for anything to happen. It's like everything just fizzles out.
Okay, yeah, not exactly a cheerful thought. So Kelvin saw this heat death as inevitable, and it shaped his view of the Earth's history as well.
Precisely. He believed that the Earth had been gradually cooling from that molten state.
Right.
And that process couldn't have been going on for billions of years, as Darwin's theory seemed to require. His calculations, based on the physics he knew, simply didn't allow for that much time.
But science is always evolving, right? Were there any later discoveries that challenged Kelvin's view of the Earth's age?
There was one major discovery that completely changed the game: radioactivity. Kelvin, of course, had no way of knowing about this phenomenon back in the 19th century.
Radioactivity. So how did that affect his calculations about the Earth's age?
Radioactivity provided a missing piece of the puzzle. It meant that the Earth wasn't just passively cooling down. It had an internal source of heat generated by the decay of radioactive elements within its core. This internal heat source kept the Earth warmer for much longer than Kelvin's initial calculations had accounted for.
So basically, radioactivity threw a wrench into Kelvin's neat and tidy estimates.
Exactly. And it's a great example of how science is a process of constant refinement. We build upon the work of those who came before us, sometimes confirming, sometimes overturning, but always pushing the boundaries of knowledge.
Kelvin, however, remained convinced of his calculations, even as evidence for radioactivity mounted. It's fascinating how even brilliant minds can sometimes cling to their beliefs, even in the face of new information.
It's a reminder that scientists are human too. They have their own biases and preconceived notions.
Right.
But what's important is that the scientific process, with its emphasis on evidence and peer review, eventually corrects these errors.
So in the end, Kelvin might have gotten the age of the Earth wrong, but his rigorous approach and his dedication to applying physics to real-world problems, those are things we can still learn from today.
Absolutely. And beyond his specific contributions, Kelvin's legacy is a reminder that science is a journey, not a destination. It's about asking difficult questions, challenging assumptions, and being open to new discoveries, even when they challenge our cherished beliefs.
We've talked a lot about Kelvin's work in thermodynamics and his fascination with the age of the Earth, but there's so much more to his story. He was an incredibly prolific inventor, wasn't he? Can you tell us about some of his other groundbreaking inventions?
Oh, tons. Kelvin had this knack for applying his scientific knowledge to solve, practical problems. He wasn't just a theorist, he was an inventor.
Right.
In the truest sense. We already talked about the mirror galvanometer, but he also developed the siphon recorder.
The siphon went now.
The siphon recorder. It was another key invention for that transatlantic cable project. Basically, it used this delicate stream of ink to record the faint electrical signals coming through the cable.
Whoa.
Allowed for much clearer and more reliable communication.
So not only did he figure out the science behind sending signals across the ocean, he also invented the tools to actually receive and read those signals.
Exactly.
That's pretty amazing.
And his inventiveness didn't stop there. Kelvin was fascinated by measurement and precision. He developed improved compasses for ships, more accurate depth-sounding equipment, even devised a way to predict tides with greater accuracy.
It's amazing how his work spanned so many different fields.
Right.
From the vastness of the ocean to the intricacies of electrical signals, really highlights how interconnected science is.
Absolutely. And his contributions went beyond just individual inventions. Kelvin played a key role in establishing standards for electrical measurement.
Oh.
He was involved in defining the unit of electrical current, the ampere, which is still used worldwide today.
So next time I'm looking at the amperage on my phone charger, I'll have to think of Lord Kelvin.
You got it. And there's another legacy of Kelvin's work that we use every day, and that's the Kelvin temperature scale.
Right.
While we might use Celsius or Fahrenheit in our daily lives, the Kelvin scale is essential for scientific research. It's a reminder of his pursuit of, absolute truth, trying to understand the fundamental nature of heat and energy.
It's mind-boggling to think that one person could achieve so much in a lifetime.
Right.
He was groundbreaking, controversial, and ultimately a driving force behind some of the most significant scientific and technological advancements of his era.
And his story is a powerful reminder that science is a dynamic process, always evolving and challenging our understanding of the world. It's about building on the work of others, asking bold questions, and sometimes even being willing to admit when you're wrong.
Yeah. You mentioned earlier that Kelvin had this idea about the heat death of the universe.
Right.
It's a pretty chilling thought, but also kind of fascinating. Given what we know today about, the expanding universe and dark energy, is that concept still relevant?
That's the million-dollar question. Kelvin's heat death concept was based on the laws of thermodynamics, as he understood them, like a universe that was a closed system. But modern cosmology paints a much more complex picture. The discovery of dark energy, this mysterious force that's accelerating the expansion of the universe, throws a bit of a wrench into Kelvin's neat and tidy model.
So maybe the universe won't just fizzle out after all.
It might not. The fate of the universe is still a hotly debated topic in cosmology.
Right.
Some theories suggest that, the expansion will continue forever, leading to this cold, dark universe. Others suggest that the expansion might eventually reverse, leading to a big crunch. We simply don't have all the answers yet.
It's exciting to think that even today, scientists are grappling with some of the same fundamental questions that Kelvin was pondering, over a century ago.
And that's the beauty of science, It's an ongoing journey of discovery, filled with unanswered questions, unexpected twists, and the thrill of pushing the boundaries of knowledge. Kelvin, with his insatiable curiosity and his willingness to challenge the status quo, embodies that spirit perfectly.
Well, there you have it, folks, our deep dive into the life and work of Lord Kelvin. From absolute zero to the transatlantic cable, from the age of the Earth to the fate of the universe, his impact on our understanding of the world is undeniable.
I encourage you to keep exploring, Read more about his life, delve deeper into his inventions, and ponder those big questions that he grappled with. Who knows, maybe you'll be inspired to make your own contributions to the grand tapestry of scientific knowledge.